So I'd like to tell you a story of how we obtained the first ever visible light picture of a gravitational wave source. And that story begins at a prospective dinner for newly admitted graduate students to the astronomy department. So I was admitted, and I was interacting with the other students and the faculty, and I see Ryan Foley. I didn't know that at the time, across the room, and I introduce myself, and I say, "Hello, what university are you visiting from, and are you planning on attending UC Santa Cruz?" And he puts his hands up and he says, "You have it wrong, I'm actually a professor." To which I chuckle and I say, "Yeah, me too." So I tell that anecdote because for me it's emblematic of our relationship ever since then. And I think that there's something that informs that. It's my path to how I got here. I myself was a student of the humanities. 15 years ago, I got a degree in history, took a left turn, learned how to program computers, and then worked in the software development industry for about a decade. In that time, I wanted something more, so I went to night school, got a degree in physics that eventually prepared me for a course of study at UC Santa Cruz. So when I met Ryan, I saw a peer as opposed to a professor. But little did I know that he is an expert observer when it comes to supernovae. So supernovae, they're the massive stellar deaths that produce remnants, and he studies these things. He studies their physics, he studies how they relate to the universe at large. What can you say about the fate of the cosmos and about its contents? And so through talking with Ryan, I became inspired to be an observational astronomer myself. He obliged, and he sent me, before graduate school even started, to Las Campanas Observatory in Chile. So get this, I am a new student, and I am told that I will go to Chile to work on the SWOPE telescope here for 10 nights. And these are winter nights in the southern hemisphere, so they're 15-hour days, or 15-hour shifts, really. So I'm there with my first introduction to astronomy using this telescope, the SWOPE telescope, a 1-meter telescope, for 150 hours. So it was pretty grueling, but right away it let me know, do I actually want to be an observer? And the answer was yes. And furthermore, it gave me this really rich physical understanding of what it meant to observe and how to conceptualize that process, which comes into play later on in the story. So I get back to Santa Cruz, and Ryan floats this idea. Why don't we hunt for the optical light counterparts to gravitational wave sources? That's a big statement, and what I want to do is unpack that a little bit. So I'm going to take you to the state of the art in astronomy thousands of years ago, and that's looking at the night sky and observing. So this was the state of the art for thousands of years, to look, to make careful observations, and it didn't really get more sophisticated until the 17th century, when Galileo turned his telescope to the heavens. When he did that, he saw the moons of Jupiter. He saw the texture of the moon as actually being mountains and craters, and there's topography. So that was surprising. Ever since then, we've been building bigger telescopes that can see deeper into space, which means we can see further back into time. And we even see colors now, colors that we can't see with our eyes, X-rays, radio waves. And that's pretty much how astronomy was, until about the beginning of the 20th century, when there was a glimmer that it could be different. And that came with Einstein. Einstein is most famous, probably, for his equivalence of mass and energy, but he's also equally famous for his conception of what gravity is. He posited that gravity is actually a curvature of space and time. So you can see this animation, this test mass moving around, changing the grid. So he thought of gravity as a curvature of space and time, and part and parcel to that theory are that gravitational waves should exist. So what are gravitational waves? Well, gravitational waves are the literal stretch and strain of space and time itself. And we ought to be sensitive to these things if we only had a good enough detector. And in fact, it was almost 100 years after their prediction that we did detect them with the LIGO detector. Now this is incredible that we not only confirmed Einstein's theory, but also with incredible precision, were able to measure distances to 1,000th of a proton to be able to get this detection. And for that, LIGO scientists received the Nobel Prize. But black holes aren't just a clever name. They're black for a reason. They're so massive, they're so dense that light can escape. So as an observational astronomer, I want something else. And neutron stars can offer that. So I mentioned earlier that Ryan was an expert with supernovae, and supernovae, they leave behind a remnant, and in this case, neutron stars. A neutron star, then, is the core of a massive star, and it's composed mostly of neutrons. And so we're talking about something the size of a city that weighs as much as the sun. And as these two objects are orbiting each other, they're bleeding away their orbital energy in the form of gravitational waves. And so as they get closer and closer and closer, they start to rip each other apart and spill their radioactive guts into space. And that produces this sort of emission that we call a kilonova, and that's what we expected to see if we ever did detect merging neutron stars. So there's a catch. If you guys will do me this solid, close your eyes, hold your hand in front of your face, and snap. Now put that above your head and snap. You can tell it's a little bit difficult to see where that sound is coming from. In the same way, LIGO detects like an ear. And so when LIGO detects these gravitational waves, you see these big air regions superimposed in the sky, and they can be hundreds of square degrees. For instance, this September 14th, 2015 region is about 230 square degrees in the sky. So basically, LIGO is saying, we detected something, we think it's over here. Right? So how do we find that as astronomers? To put this in perspective, the full moon is a quarter of a square degree. So if I shrink this full moon on the scale of those regions on the map, well, you're not going to see it, because there would be almost 1,000 full moons that could fit into that September 14th, 2015. And the story gets a little bit richer. There's a David and Goliath aspect to this, because some of the major collaborations that are looking for these signals are actually spanning a dozen institutions, and they have huge telescopes, and they have hundreds of scientists. And to kind of put that into a visual, here's the Blanco 4-meter telescope compared to the Swope telescope, that red square. So we're talking about the Blanco telescope having 16 times the light collecting power and 12 times the field of view. So they're roughly getting 200 times more photons or packets of light than Swope is. So how can we compete with that? Well, like David versus Goliath, we compete with that with agility and cleverness. So in particular, our collaboration is called the 1-meter 2 hemispheres collaboration, and it consists of a telescope at Lick Observatory in California, and that's associated with the University of California, and the Swope telescope in the south that I already mentioned. In addition, instead of brute force imaging that entire region that we saw, which would pretty much be a fool's errand with looking through a straw telescope, instead we're going to target where most of the mass is. We're going to target the galaxies, and it turns out that the universe is clumpy. So we can make intelligent decisions about where to look as opposed to just mowing the lawn, as it were. So it took me about a year to put together this idea in the form of software tools and an actual protocol that we could follow if LIGO sent us an alert. This is an image of the Niels Bohr Institute in Copenhagen, Denmark. So about a year after my time in Chile, this last August, Ryan and I found ourselves at the Niels Bohr Institute at, serendipitously, this basically workshop for gravitational waves. Now, I was there in a different capacity, doing my own research, and we worked like dogs for a few days, and then we took a holiday. So Ryan decides to go to Tivoli Gardens with his girlfriend, and I decide to go to the Louisiana Museum of Modern Art. So, ticket in hand, walking out of the door, the universe had different plans. So, as I was walking out of the door, I received an email from LIGO saying that there was a new detection. And not just a new detection, 2 neutron stars. Okay, this is the holy grail detection. And it had a false alarm rate. So the way that LIGO quantifies how much they believe their detection is by describing it in terms of a false alarm rate. This false alarm rate was 1 in every 10,000 years. So 1 in all of the civilizations of Egypt combined, did they think that they were wrong? In addition, we can see here on the top data from the Fermi telescope, which is a space-based gamma ray detector, and LIGO on the bottom. So prepare yourselves, you're about to hear a gravitational wave and a gamma ray burst. On the bottom, you can see this crescendo in cyan, which is the LIGO detection. And believe it or not, that's actually what a gamma ray burst sounds like. So this is so extraordinary because I had just gone to a lecture where Ryan told me that it was unlikely in the next decade that we were going to see a gamma ray detection associated with a gravitational wave detection. In fact, we might not even see it in our lifetime. So this is absolutely bananas. And speaking of bananas, here's the yellow banana that corresponds to the LIGO uncertainty region. Now, I made this analogy between our hearing and how LIGO detects things. Well, it turns out that there was also another detector called Virgo in Italy that had a hand in this detection. So imagine having 3 ears, you'd be able to triangulate things much better. So because of this, we went from hundreds of square degrees in uncertainty to about 30 square degrees in uncertainty, which is definitely a tractable problem with the 1 meter telescope. Okay, so all of a sudden, the race is on. About 60% of the world's astronomers are all looking for this thing at the same time. And where am I? I'm in Copenhagen without phone service, and my boss is on a date. So I text him, stop what you're doing, please. There's a neutron star detection. I give him the spiel about 1 in every 10,000 years. There's coincident neutrinos, gamma ray burst. And he says, this sounds like a joke. So we go back and forth, and I'm trying to implore him, convince him, with reasoned arguments that this is actually a real detection. And in the process, I am making hamburger of my coordinate transformations, and he thinks that I'm just messing around. So it gets colorful, so I apologize for that, but you have to understand the moment. And it ends with a supplication that finally does change his mind. So Ryan comes to the office. And by this time, you know, the sun has set and moved on from Africa, and now the night is creeping across the Pacific Ocean, and we're waiting for night to fall in Chile. So we've got 10 hours before we can even start looking. But what I want to draw your attention to here is a sky map from the perspective of the SWOPE telescope. The shaded region you see is actually below the horizon, so there's no hope for SWOPE to see that. And the red little gash on the side, that's the LIGO uncertainty region that we want to search. And if you look at this red arrow, and it's moving from your perspective to the right, the whole map is going to translate that way over time. And really, we only have an hour to look for this thing before it dips below the horizon. So, okay, we waited 10 hours. We furiously were putting together observation lists. I was taking all this knowledge that I had gained over the year of building this pipeline, and we had an hour to find it. And you can imagine there was an intensity, there was a fervor to trying to get everything together. So the situation is we have astronomers at Santa Cruz that are actually receiving the data from the telescope, reducing that data and comparing it with archival information to see, hey, is there something different? And then we also have me and another graduate student and Ryan in Copenhagen actually at the Nerve Center typing things to people in Santa Cruz, but also communicating with the observers in Chile to make sure that they observe things in the right way. And so I just want to prepare you for a lot of motion right now as our chat log goes forward. So this is us chatting, bundling targets together, downloading data, and this is Charlie, who is in Santa Cruz saying, okay, nothing in this field, nothing in field 12. And then here you go. This is the moment, I think, when the hairs on the back of my neck stood up. Found something. And you can see that I'm speechless. It's just an exclamation point. I've lost the words, and in some ways, I still don't know how to accurately describe the feeling. And I think the best visual I have for communicating to you what the feeling is like is an image of my daughter that I just had a couple months ago. This is her. And she still makes this face when I recall this story and I tell her how I messed up my coordinate transforms. So here we are. Charlie sends us this data here, and this is the before image. This is the image before our image. And then he sends us this. And that might have been hard to see, but there actually was a point of light there that showed up in that image. So I'll make it bigger for you guys. So here, this is the discovery image of a new kind of astrophysical transient. And it's easy to see which one of those points is the actual object because, well, one second. Because there's a red arrow. Okay, but in all seriousness, this archival image, we happen to be lucky enough for the Hubble Space Telescope to have imaged this field some months prior. And you can see on the left, there isn't a dot where the arrow is. On the right, there is. So it's just as simple as that. When you write a discovery paper, you basically said, we looked, and it was here. So I want to go back and I want to emphasize the team that made this discovery. Okay, so you're going to hear from Enrico right after me. But there's Ryan, and you guys have seen his picture. Everyone else in that slide is a first or second year graduate student or a postdoc. I think that's remarkable. We had a 1-meter telescope. We didn't have a 4-meter telescope, right? I came into this program without a huge amount of, sort of experience, but I was able to make a significant impact coming into a department like Santa Cruz's. And I think the image that really typifies that is the fact that we got the breakthrough of the year. So to give some more details on that, I'm going to have Enrico come up to the stage and talk about what this means.
So I'm going to tell you why there's an August 17th event in all of us. I'm going to take you through the history of gold production and element production in the universe, and hopefully I will convince you that we ourselves are the fossil record of chemical evolution in the universe. And of course, I'm going to use Carl Sagan's words, which says, the beauty of a living thing is not the atoms that go into it, but the way that those atoms are put together. So we are atomically unbelievably numerous. There's more atoms in our body than actually stars in the entire universe. We have 10 to the 27 atoms in our body. Yeah? And those atoms have a vast memory. Yeah? You can talk to your hydrogen atoms about the Big Bang when they were first produced. Yeah? You can talk about the helium atoms also about the Big Bang and the first 3 minutes in the history of the universe. And you can talk about all the generations of stars that have ever been formed, exploded, and recycle those atoms, yeah, all the way until today, that are now sitting in our bodies. So we are slightly different than the universe in the sense that the majority of our mass is actually made of oxygen. We're 65% oxygen, 18% carbon, about 10% hydrogen, which of course, as you know, is the most abundant element in the universe, which was made in the Big Bang. And we also have a significant amount of nitrogen. And each of these elements has a story on its own. And of course, because I don't have as much time, I'll tell you about, of course, the most important element, because we are, as humans, self-centered, which is oxygen first. So, the oxygen that we breathe, the oxygen that made the majority of our body, was in fact catalyzed in a massive star, in a star that it's about 10 times the mass of our sun. It has about 1,000 times its luminosity. These stars are sort of the Elvis Presley of the universe, They're extremely luminous, but they live very short lives, because they exhaust their fuel so rapidly. One of these stars has about 10 to the 58 atoms, and they fight their struggles against gravity. Gravity wants to compactify the star, and the star is actually going into nuclear reactions into the interior, generating heat and preventing gravity from winning that battle. And that fusion of elements goes all the way to iron. And iron, as you know, is the most stable nuclei in the universe. And that means that the battle is basically lost. Gravity has won. No more fusion can actually take place that gives energy to the system, and the star collapses. And it is in that collapse that a neutron star is actually formed. So I'm going to show you a simulation here of the core of this massive star. And again, in the core, everything is happening very quickly. You can see in a fraction of a second, the majority of oxygen in your body is going to actually be produced. What you're seeing here is entropy or temperature. So the temperature is increasing. Energy is being accumulated in the core of the massive star. The entire core is basically collapsing. So there's material constantly falling in, heating up this interior until enough energy actually is confined that you go from an implosion to an explosion. And so much energy is actually generated that it basically tears the entire object apart and leaves this neutron star in the core. And it's in that edge that you see where actually the majority of oxygen is explosively made. One of these supernova explosions, like the ones that David and Ryan studies, when it explodes, it's actually as bright as the entire stars in a galaxy put together. And that's how we can find them. We can go closer to home and look at these beautiful supernova remnants. And I want you to visualize that the majority of the mass in your body came from one of these supernova remnants. The oxygen here was basically ejected into the gas, mixed, and then gave rise to new generations of stars. So we are a constant recycling of these steady, beautiful luminosity to this violence to rebirth again into new generations of stars. In our bodies, we have about hundreds of thousands of supernova, at least the memory of it. Now, oxygen in particular is one of my favorite elements because it's constantly recycling the atmosphere. The atmosphere actually doesn't lose a lot of oxygen, so then you can think about, well, not only the universe is recycling oxygen, but we are recycling oxygen. I go about 550 liters of oxygen a day, all of us do. I'm lucky enough to be standing in front of you and stealing some of your oxygen atoms that you came in with, and I'm going to take them away. And I'm hopefully sharing you my good oxygen atoms. So what does that mean? That means that we're not only the fossil record of the universe, we're also the fossil record of humanity. So you can do a calculation and say, well, how many atoms I have of Shakespeare? Well, about 1 million atoms of oxygen in my body once belonged to Shakespeare. About another billion of atoms in my body belong to Frida Kahlo or to Cesar Chavez. And of course, you can think about the atoms that you don't want to know. But you can choose and pick your atoms. So that means that all this unleashed creativity of humanity is actually in our bodies. And the reason is because we are atomically so numerous. And then we go to sort of the central theme of our talk, which is gold. In that beautiful shining light that Dave and Charlie saw for the first time, we also saw the production of heavy elements, and in particular gold. What it's giving power to that source was actually the radioactive decay of heavy metals, and in particular gold. So Dave is sort of an alchemist in the sense that he's not making gold, but he's deciphering the origins of gold. And as I hopefully will guide you, actually coming up with the recipe of gold really is beyond humanity, because these systems require the largest densities in the universe and the largest temperatures ever to be manufactured. And then you say, well, you convinced me that I should care about oxygen and I should care about supernova explosions, but you should also care about gold, because we have about 10 to the 18 atoms of gold in our body. And if you like sushi, you probably have higher concentrations of gold in your body. So gold is not highly abundant. Here in this table, I show parts per billion. So the universe is about 0.6 part per billion by mass of gold. The sun is about 1 part per billion in weight. Meteorites are actually highly enhanced in gold. They're about 170 parts per billion. And one of the reasons why we actually want to go and mine asteroids is because they're highly enhanced of these precious elements. Crustal rocks also have significant enhancement. But if you ask yourself, where is most of the gold today that it's actually available for extraction, it's actually in seawater. But seawater has very small proportions of gold, about 0.05. And thankfully, humanity hasn't found a way to actually economically feasible extracting that gold. But we humans are extremely metal rich. Compared to the universe, we're 50 times more abundant in our gold content than the universe. Yeah? So we are precious. If you actually think about sort of the quantities, all the gold that has ever been mined is about 160,000 tons, which is about the size of 10 buses. Yeah? And the majority of that gold is in a vault, and only about, a few percent is actually done for jewelry. So I have to go back to my origins and give credit where credit's due. The Aztecs actually thought that the origin of gold was the sweat of the sun. They thought the sun was sweating these pieces of gold that we can find highly concentrated. And you can say, well, Enrico, but you told me the gold is 1 part per billion. Then I could be walking around, especially at the time of Shakespeare, and find these gold nuggets. Yeah? And that's because in these crustal flows, gold gets highly concentrated at high pressures. And that's why it's easy to find. Well, the Aztecs were not completely wrong, because there are a significant amount of gold in the sun. As I said, 1 part per billion. So how much gold there is? Well, if you extract the entire gold of the sun, you get about the mass of Ceres, which is the largest asteroid in the solar system. This is to give you a perspective. It's about 900 kilometers or so. Oops. Too sensitive. So this is the price of the sun in gold. Yeah? And this is about $10 per gram. So this is the price of the sun in gold. And I'll tell you a little bit about the price of Dave's discovery. So for 15 years or so, I have been working on this idea of how gold is made, this recipe of gold. And the ingredients are, we need the densest object in the universe. It has to actually have a companion, which also happens to be the densest object in the universe. You have to merge them together at billions of degrees Kelvin, and then gold will come out. So neutron stars, as David mentioned, they are the size of the San Francisco Bay, but the mass of the sun. So they're the densest objects of the universe. If I was sitting in the surface of a neutron star and I wanted to escape, I have to move at 30% of the speed of light to be able to escape the gravitational force from that object. Yeah, they're the densest objects in the universe. They're rare. A bucket of neutron star material weighs as much as Mount Everest. The density of neutron star material is about 10 to the 14 in units, where the density of water is 1. So they're 14 orders of magnitude denser than water. About 2% of all neutron stars are members of a binary system. That means that they're orbiting around a companion, and they have basically a company throughout their they're burning heavier elements, about 1% of those neutron stars have another neutron star. So it's the 1% of the 1%. So 1 part in 10,000 of all neutron stars in the Milky Way, which are about 100 million of them, happen to have a companion. So they're very, very rare objects, and that was one of the reasons why this theory was actually put into question for a long time. These objects spend about 1 billion years orbiting around each other, losing energy and angular momentum through the emission of these gravitational waves as they distort space and time, slowly coming together. Until they basically become what we call dynamically unstable. They sort of collide with each other. They increase their temperature to billions of degrees Kelvin, and this is where we think gold production actually took place. I'm going to show you here one of, the sensitivity of this device is letting us down. I'm showing you here the last in spirals of 2 neutron stars. This is a computer simulation that took about 2 months in 1,000 processors. What you're seeing there is temperature or entropy. So these objects touch each other, eject material in what we call these outer Lagrangian points, these beautiful spiral tails. And it's in those spiral tails as they move away where gold is actually produced. And that was the theory. Yeah? So it was an extremely rare event that produced a lot of gold. And that was one of the reasons why it was put into question. In fact, if you open any textbook, it says that the majority of heavy elements in the universe above iron come from supernova explosions. The same supernova explosions that give rise to your oxygen. So for the past decade or so, I've been working on this subject and getting some interesting email from my colleagues about how it's completely crazy that the majority of the gold in the universe actually assemble in these very exotic events. This is about January 2011 with a world-renowned astrophysicist, which we'll rename nameless, that says the idea that mergers are able to enrich the universe with heavy elements must be rejected as a physically impossibility. Yeah? And it took us about 5 years to convince that our argument was indeed incorrect. And at about April of 2017, The Atlantic published an article which says the mysterious origin of our galaxy gold. And it says, after long believed that exploding stars, supernova, forge these metals, researchers now are divided over which extraordinary cosmic event is truly responsible. So that means that, after a decade or so, we were just starting to accumulate clues that, in fact, we may be right. And there's a beautiful quote by a good friend of mine that says, if LIGO, this amazing instrument, still has not found something, there'll be a moment in which myself and my colleague Brian, which were quoted in the article, should wander and get back to the board. That means you should do something else. You have devoted a decade of your life, you may be wrong, and you have to start facing the consequences of that. And of course, August 17, everything changed. And I was lucky enough to be part of this wonderful team. I'm a fake astronomer. That means I don't look up at the sky, I look at my computer screen, but I get to work with these amazing colleagues of mine. And the glow that you're seeing of this source is really powered by the radioactive decay of precious elements, things like gold, platinum, silver. Yeah? So this is sort of the dream of astronomy. For about 30 years, half of the elements heavier than iron, we didn't really know their origin. And now, thanks to this wonderful group at UC Santa Cruz, we now know the origins and we can pinpoint it. It is breathtaking to me to think about the creativity and strength of our group. Dave mentioned that, we were sort of the underdogs, but I felt, we basically use strategies in place that will get us ahead of the game. And one of those strategies at UC Santa Cruz is actually invested in our youth. If you look at the students that are represented here, we have Cesar, who's from Costa Rica. We have David, of course, who is not a non-traditional student in the sense that we were able to lure him back to science. We have Ariadna, who's from Mexico, Matt, who is an incredibly talented undergrad student. We have Enya, who's from Serbia, or formal Serbia, and then we have Charlie. And a testament, really, of my colleague Ryan Foley is that we publish 6 papers, 6 really breakthrough papers, and every single one of those is actually led by a grad student or a postdoc. They had, as you can see, the entire glory of this discovery, and they deserve it because they did all the work. So in Santa Cruz, we do invest in students. So how much gold is created in one of these events? So this is actually what we set up to do. And here you see, this is a Nature paper with my colleague Brian, which was named in that article. Well, one of these events produced about a Jupiter mass of pure gold. I mean, remember, you immediately say, well, but in the sun, there's about a Ceres mass of gold. What's going on? Well, one of these events produced a huge amount of gold. And in fact, it's enough to supply of precious elements to about 6 million stars. Yeah? So this was actually one of the arguments why people were very skeptical that these rare phenomena could produce as much gold in order to supply the entirety of the galaxy today with these precious elements. And of course, these led to the breakthrough of the year, and I have to really talk about Dave, even though he doesn't like to be talked about. Dave basically wrote the most important article in the Science journal, which now has about 110 citations. His paper has been cited, more than once every day since it was published. There's always a scientist in the world that is getting to know Dave. And it's really a testament to his perseverance and his creativity. Yeah? I mean, he made it happen. And, I'm really, really grateful that you proved me right. Now I can retire, so thank you, Dave. So I wanted to just take you to a final journey as to, where ultimately that gold and how that gold ultimately comes to us in this sort of journey of recycling of metals. So as you know, all of these explosive phenomena throw out metals all the way into the universe. They get mixed with gas and new stars are formed. What you see here is the formation of our solar system, where the sun was actually formed from this rotating cloud, which created this sort of pizza structure where basically our planets are made. But something that is extremely interesting is that when the Earth was actually made, it was molten, which means that all the heavy elements sank into the center. And for a long time, people actually debated, well, where is the gold that we find in the surface? Where does it come from if all the gold on Earth is actually at the core? And the answer is, it came from the late bombardment. It came from basically asteroids that impact the surface of the Earth. As you know, asteroids are about 200 times more abundant in heavy elements, and therefore they sort of painted the surface of the Earth. Those metals mixed in the mantle, concentrated, and then came back, and that's where we basically built mines. So in the spirit of Santa Cruz, I thought it was fitting to end my talk giving you a myth. Yeah? This is a myth from the Olmecas. If you don't know the Olmecas, they're this Mexican culture that have these beautiful sculpted faces. There are these huge sculpted faces in Veracruz. They have very, very small noses. A lot of people say that I look very Olmeca and make fun of my nose in Mexico. That says the following: at the moment you are conceived, your essence, as it tries to reach you, breaks into a million pieces. So the same way that the gold is ultimately delivered to Earth by asteroids, your essence is delivered to you, but it's basically broken into a million pieces. And my grandfather used to say, well, but one of the consequences of that is that when you start, gaining consciousness and realizing who you are, you're going to feel slightly incomplete, slightly empty. But that's actually an opportunity, because those pieces, rather than basically be scattered around and you having to pick them up from the streets, fell into other people. And it's only by sharing those pieces with other people that you become more complete. Yeah? And the natural consequence of that is that every single piece is important in your journey to become complete. And there are going to be people that are going to give you these very, very large pieces and are going to make you very happy. And there's people that are going to give you smaller pieces, yet they're going to be necessary for you to be complete. And to me, that really captures the essence of what UC Santa Cruz is, and the belief that we have in our students, and the way that we contribute all together in science. So hopefully the next time you look at your gold ring, you will remember that in order to produce that ring, it took the two densest, most exotic objects in the universe that happen to live together, that happen to meet almost their entire rest mass energy in gravitational waves to come together, to be merged in billions of degrees to ultimately make gold. And I'll stop there. Thank you.